In this video, we're going to talk about frictionless pin assemblies or hinge assemblies. And we have two parts as part of the assembly. One will this block, which has a circular element called the pin. And we'll assume for the course of this all discussion that this block element, this is rigidly attached to the earth. So if I put any force acting on this pin, this whole assembly, that there's no motion, or if I try to rotate it, that this part is immovable, is fixed. And the second part of the assembly we'll call it a seesaw element, which is our block that has a hole in it. So that's the mating element to this pin. And we'll assume it's frictionless, and so we'll assume that there's any torque or that wants us to rotate, that this part will continue to rotate about the center point of that pin infinitely at the same rotational velocity. So what's the purpose of this? If it doesn't prevent rotation, well, it prevents translation. So if I put a force through this block element to the side, and I have that force acting in a vectorial direction passing through the center of the pin, well, then there's no translation of this block element to the side. If it wasn't through the pin, if I put a force on the side of it, this block would just accelerate to the left. Okay. Likewise, if I put a force on the top here, acting through the center line of the pin, there's no translation. This block element doesn't go down because there's a reactionary there's a paired force between the block and the pin, and between the block that reacts to counteract this downward force here. And so if I had a force at any vectorial direction, for example, force acting here, that acts through the center of the pin, there is no translation. The block doesn't move this way because there's a reactionary force in the center. So pin joint has reactionary forces that prevent translation of this part, well, to the left and right, up and down, as well as in and out of the board. But there is no, if we assume frictionless, there's nothing that resists any torque. So that even the smallest amount of force acting on the side will cause rotation. This is the free body diagram approach to the same problem. So again, we had this block which had a pin on it, and I had a hinge assembly, so I had a part that was potentially free to rotate in a friction around the frictionless pin. So this is our seesaw on the assembly, this fixed assembly, and the seesaw which potentially can move. Okay, so what a pin does, or this frictionless hinge, provides reactionary force to prevent translation of this seesaw assembly, but it provides no force or torque which oppose rotation. So potentially it's free to rotate about the center. So in this problem, let's assume that the center of mass of the seesaw assembly is in the center of this part, and that's right where the hole is. And we have a arbitrary force, magnitude F1, and we talked before, we're going to have that force acting right through the center of the pin. And so I had this force 1, it's angle beta 1, but it's going line of action of that force, that vectorial force is through the center of the pin. So now if we draw a free body diagram just of this block element, the seesaw element, what we have is think of all the forces that act on it. Well, I have this external force acting at angle beta 1 going through the center of the pin. It has mass, so I have gravitational, so I have the mass of the seesaw times g, and that's also going through the center of the pin because I said that's the center of the mass, the element is through that element right there. Well, is that the only forces I have? No, I have, if that's all I had, then this thing would go flying through space. It would want to fall because of the gravitational force, and would want to go in this direction because of this force. So the pin is doing something to react against it. So the pin's providing some forces to prevent motion up or down, or in and out of the board. Since I didn't have any force in and out of the board, we're just going to look at it in this plane right here. So I just drew arbitrary. I said there's a force on the seesaw by the pin in the y direction, and there's a force on the seesaw on the pin in the x direction. And I drew them. I was assuming I'm going to have probably some force that's going to react against this force, so I drew that one in this direction as shown right here. So think about it. Do I have any other forces acting on this? No, I don't. So that's my free body diagram of this element. And now I can pick a coordinate system. I just picked the Cartesian general coordinate system, horizontal x, vertical is y. And now I think about accelerations. So is this, in this assembly, if I hold this to the earth and I push on it, will this seesaw element be accelerating up or down, translating up or down, or to the side? Well, it's not. So my acceleration in the x direction is 0, and my acceleration in the y direction is 0. So now I can start writing my Newton's first law, second law. So let's look at the sum of the forces in the positive x direction. So, and that's the mass of this element times its acceleration. Well, I know it's not accelerating horizontally, so that magnitude, that mass times acceleration has to equal 0. And look at all the forces right here. So I have a component. This component right here is horizontal, and then I have this reaction force of the acting on the seesaw by the pin here. So I can solve for the magnitude of that reaction force. Then I can do the same thing in the sum of my forces in the positive y direction. That's the mass of the seesaw times the acceleration of the y. Well, we know this, the seesaw can't accelerate up, so that sum has to be 0 because that goes to 0. So now let's do all the forces. I have this component of F1 going upward. I have gravitational force down, and I have this reactionary force on the seesaw by the pin. So I can solve for this reactionary force to these unknown forces. So now so now I know what force is acting on the pin, and likewise, what's the paired force that acts at the pin joint on the seesaw. And the last thing I want to look at is rotation. And so for rotation, we'll use similarly to sum of the forces equals mass times acceleration. We'll use sum of the torques is moment of inertia times angular acceleration. So we'll call this a counterclockwise is our general rule of positive. So we'll pick a point. You have to pick a point. So we'll call this. We'll look at this the torques acting around the center of that pin. Okay, so that's moment inertia times the rotation or acceleration around the center of that pin. And so that's going to be so look at each force. So the mass, this force right here, mass times acceleration. And then what's the distance between that force vector and my point, my center of the pin? So what's that distance? Well, that distance is 0 because that force goes right through it. So that's 0. And then I have this vectorial force F1, which I said, so here's this magnitude, and what's its perpendicular distance of that force vector relative to the center of this point, center of the pin where I just selected it? Well, that's 0. And then I have my X force, reactionary force between the seesaw and the pin. Well, so that has a magnitude, but what's its magnitude? What's its perpendicular distance? Called d. You could also call it r between there. Well, that goes to 0. And likewise, this one, there's no distance. So there's no net torque. Since that's something to be 0, that's 0, so no net torque, which means my angular acceleration is 0. So this is not going to accelerate in the rotational coordinate system. This is a continuation of the problem, but I've changed two things in this example. One thing, I changed that this external force that's acting, now I have it not passing through the center of that pin element, but it's passing up above it. And the perpendicular distance between the center of the pin and where that force is acting, we'll call r sub 1 perpendicular. The other change I made was I made the center of mass of this block element be different than where the pin is. I offset it to the side, so there's center of mass is off to the side. And so now we'll solve the problem, the exact same thing, to see what forces and possible accelerations are happening on this object and see what changed. So I drew my free body diagram. It's the same forces that were acting before, just I drew it now so that I had these perpendicular distances between force B1 and the same thing force here. So now again, that's all the forces acting on it. We still have reactionary forces as shown. And we'll solve for some of the forces X, and nothing changed as before by moving those locations. If we do some of the forces in the Y direction, we'll see nothing changed. I get the same reactionary force. But now if I do the sum of the torque about the center of the pin, positive direction, is the moment of inertia times the rotational acceleration. So this gravitational force down now, if I think it's got to route the pin, it wants to rotate this block around this way because its force is off the center. It wants to rotate it this way. So that's in a clockwise or negative direction. So that force times that radial distance between the line of action of that force and the center of this, I'm doing the torque about the center of the pin, so that's a negative. So it's the force magnitude times that mg times that radius between the vectors, and the vector force and the point where I'm trying to do the torque about. Okay, same thing here. So that's not a zero term anymore. This force 1, again, that force is acting here, trying to spin, put a torque on this block. It's torquing this block to make it rotate this way, which is I'm defining that to be a negative. So it's minus that magnitude times that perpendicular distance between that force and the line of action of that force and the perpendicular distance that goes through the point, which I'm describing, the center. And then I have the two reactionary forces, and those forces, they go through the center of the pin, so they have no distance, so they turn out to be 0. So those go away. Now I can solve for the angular acceleration of the part. Okay, so I'm going to get this equation right here, these terms right here, and they're both negative. So both of these forces, these torques, this force times the distance, these torques are making it turn this way. So both the gravitational torque and the torque as shown right here is making this part accelerate. So it's going to be accelerating faster and faster rotationally at this rate of angular acceleration. Now on this problem, if we changed it and said, well, let's say the seesaw is not rotating. There's going to be some, so it has the center mass, but what force acting in that vectorial direction would cause it so it would have no rotation. So if it had no rotation, then the angular acceleration would be 0. So 0 would be equal to this quantity. So I changed the problem and I said I want to have no rotation taking place. This is in static equilibrium. It's not moving. So now 0 equals this, the numerator. So that numerator has to be 0. So 0 equals that. So I can solve for f of 1, that's external force. So it's the magnitude of the gravitational force, mg, times the perpendicular distance to the center of gravity and the center point of my pivot, divided by this distance. And that would be negative. So it would say this force would be acting in this direction to counteract this, and then it would be equilibrium and it wouldn't be moving.